This video will showcase two examples of taking the length of a curve using integration. Welcome to Integral Calculus. The first example involves the function y is equal to 2 times x raised to 3 halves over the interval from 0 to 1. For lengths of curves, it is not required to draw the curve, so all we gotta remember is the formula for L, which is the integral of the root of 1 plus the square of the derivative times dx or dy, where the integral is from b to a. With a given function in terms of x, and also the interval in terms of x, it is just right to use dx in the formula. So let's start the solution. Y is given as 2x raised to 3 halves, and its derivative dy over dx is twice of the derivative of x raised to 3 halves, which is 3 halves times x raised to 3 halves minus 1. Giving 2 times 3 halves times x raised to 1 half. Cancel out the 2's and have dy over dx as 3 times the root of x. The next thing to do is to plug this derivative and the limits in the formula. So we get the integral of the root of 1 plus the square of 3 root of x dx with limits from 1 to 0. Expand the square and have L as the root of 1 plus 9x dx. Now focus on 1 plus 9x. Some might be thinking of solving it with trigonometric substitution, but then 9x is not a perfect x squared material, so we should work on another integration technique. Let's use integration by substitution and have u as 1 plus 9x. Its derivative is 9 times dx. With the 9 on dx, adjust the integral by multiplying 9 on dx and 1/9 before the integrand. With everything in the integral already balanced, we can substitute u to have L as a ninth of the root of u times du. Take note that the limits are not yet placed, as they are to be transformed in terms of u still. So with the ninth of the root of u times du, complete the integral by transforming the limits in terms of u. Take note that u was assigned as 1 plus 9x. So at x equal to 0, u is 1 plus 9 times 0, which is 1. So the lower limit stays at 1. Then, when x is 1, u becomes 1 plus 9 times 1, and that is 10. This is the new upper limit. So the integral is completed as 1/9 of the integral of the root of u du from 10 to 1. With everything in the integral transformed in terms of u, we are ready to integrate using the general power formula. L is then integrated to contain 1/9 of u raised to 1/2 plus 1 over 1/2 plus 1, and this is within the limits from 10 to 1. Simplify the expression to have 1/9 of 2/3 of u raised to 3/2 from 10 to 1. Simplify the constants and substitute limits and get 2 over 27 of 10 raised to 3/2 minus 1 raised to 3/2, which gives the final length of curve as 2 over 27 of 10 root of 10 minus 1, or 2.268 units. The second method of integrating the function is to retain the limits but then we transform u back into x. Let's get back a few steps before the transformation, when we had L as equal to 1/9 of the root of u du. Integrate the function by general power formula and have 1/9 of u raised to 1/2 plus 1 over 1/2 plus 1, which can be simplified as 1/9 times 2/3 of u raised to 3/2, and even simplified further into 2/27 of u raised to 3/2. This is the final u, and we need to revert this back in terms of x, based on the assignment earlier, which was u assigned to 1 plus 9x. Place this u into the final L to have 2 over 27 of the quantity 1 plus 9x raised to 3/2 with the limits from 1 to 0. Substitute these limits to have 2/27 of the quantity of 1 plus 9 times 1 raised to 3/2 minus 1 plus 9 times 0 raised to 3/2. This can be reduced to 2/27 of 10 raised to 3/2 minus 1 raised to 3/2, which gives the same answer of 2.268 units. Look at the second example, which is seemingly similar with the first. The function is y as equal to x squared over the interval of 1 to 3. The length of curve uses a formula, and we are to plug in the terms. Take note that the interval in the given refers to x as 1 to x as 3. Start with the function y as x squared. Its derivative dy over dx is 2x. Place the limits and the derivative in the formula, so we get L as the integral of the root of 1 plus the square of 2x dx from the limits of 3 to 1. Expand the square and get 1 plus 4x squared inside the radical. Focus on the term inside the radical, 1 plus 4x squared. Due to the exponent of 2 on x, the derivative required is 2x dx, where we are lacking x, so we cannot use u substitution, but we resort to trigonometric substitution as the quantity has the pattern of a squared plus x squared. Having a plus sign between the terms, we are looking at using x as equal to a tangent theta. But we still need to figure out what a is. We need to simplify the quantity in a squared plus x squared, which means there should be no coefficient of x squared, because right now there is 4 before x squared. We eliminate 4 by dividing the quantity by 4, so the 4's cancel out, and we have the root of 1/4 plus x squared dx. At this moment, we can now identify a from the formula x equal to a tangent theta. If a squared is 1/4, a is then 1/2. So x is written as 1/2 tangent of theta. Also take the derivative, which is 1/2 times the derivative of tangent, which is secant square theta. There are two ways to proceed in trigonometric substitution. We start with interpreting the formulas into a triangle. So using a right triangle and assigning one of the smaller angles as theta, we identify the sides to use trigo functions later. With the reference in general form of a squared and x squared, the legs of the triangle are a and x. So using Pythagorean theorem, the hypotenuse is the root a squared plus x squared. So the root of 1 plus 4x squared is the hypotenuse of the triangle. The next thing to figure out is which is the adjacent and the opposite sides. From the formula x as 1/2 of tangent theta is x all over 1/2, or 2x, all over 1. Tangent is opposite all over adjacent, so 2x is the opposite side from theta, and 1 is the adjacent. First, we take secant of theta, that is the hypotenuse all over the adjacent side, which are the root of 1 plus 4x squared all over 1, or simply root of 1 plus 4x squared as secant theta. And also, the derivative of x has been figured out earlier as 1/2 of secant squared of theta d theta. So from the original function of root of 1 plus 4x squared, we can transform this into secant theta for the term in radical, and then 1/2 of secant squared theta d theta for dx. Simplify this as half of the integral of secant cube of theta d theta. This time, we will leave the limits blank, as we should also transform them into terms of theta. We do just that using x as half of tangent theta, where tangent of theta is 2x, and theta is extracted as arctangent of 2x. So if x is 1, theta is arctangent of 2 times 1, which is 1.1071. If x is 3, theta is arctangent of 2 times 3, and that is 1.4056. With everything complete in the integral, we can then move on and integrate it. The integral of secant cube theta is half of secant theta, tangent theta, plus ln of secant theta plus tangent theta. It is quite a bunch to remember, but it would be best to have the integration be memorized. You can take out all of the constants out to the left, but the next step is to plug the limits, where we place the upper limit of 1.4056 into the equation, and then subtract the term with the lower limit of 1.1071 plugged in. Although long, work on the answer using your calculator and have the length of the curve determined as 8.2493. This is the answer using rounded off limits, so there could be some discrepancy on the decimals based on the rounding off of the limits and the substitution. What if one finds using the triangle confusing? You can still find the length by just substituting terms. So we are back to the original function of the integral of the root of 1 plus 4x squared dx from 3 to 1. We also figured out that x is 1/2 tangent of theta, and its derivative is 1/2 of secant squared theta d theta. Simply substitute these equations into the original function. So the radical covers 1 plus 4 times x squared, which we change into half of tangent theta. Then insert dx, which is half of secant squared d theta. Expand the quantity with square, and the integral becomes the root of 1 plus 4 times a quarter of tangent squared theta. The derivative still remains the same. Cancel out the 4's and have the function reduced into the root of 1 plus tangent squared theta times 1/2 of secant squared theta d theta. Focus on the quantity inside the radical sign, 1 plus tangent squared theta. If we use Pythagorean trigo identities, which is sine squared theta plus cosine squared theta as equal to 1, then we divide this by cosine squared, we get tangent squared theta plus 1 as equal to secant squared theta. So we can convert the binomial inside the radical into a single trigo function, which is secant squared of theta. Then we take the square root to have simply secant theta. So the function becomes 1/2 of the integral of secant theta times secant squared theta d theta. Combine the secant functions to shorten the equation into 1/2 of the integral of secant cube theta d theta. Like what we did earlier, let's just transform the limits in terms of theta, using x as half of tangent theta. Transpose 1/2 and have the tangent of theta as 2x. Then theta is computed as arctangent of 2x. So to transform, we plug x as 1 for the lower limit. Theta is then arctangent of twice of 1, and that is 1.1071. The upper limit has x as equal to 3, giving theta as arctangent of twice of 3, and that is 1.4056. The integral is then complete. L as half of the integral of secant cube theta d theta from 1.4056 to 1.1071. From the reduced function, we are ready to integrate. And again, the integral of secant cube theta is half of secant theta tangent theta plus ln of secant theta plus tangent theta. This would be quite long to read per term, so we simplify the discussion by saying that we plug the upper limit of 1.4056 into all the thetas, and then subtract the same term with the lower limit of 1.1071 plugged this time. Compute the values carefully, and you should arrive at 8.2493. Or close to the answer as deviations of rounding off's decimals.